Good afternoon to all of you. We will start with our tutorial session on dynamics of viscous flows, and today we will address the problems on internal flows. So, internal viscous flows, and the agenda of this session will be as follows. In the first part we will discuss about the tutorial problems and some hints for solving the tutorial problems, and then we will take up questions on dynamics of viscous flows. So, I will hand it over to Dr. Sukumar Poti for discussing the tutorial problems.
So, good afternoon. So, coming to tutorial problems, first problem, just please go through the problem. Consider steady fully developed laminar flow of oil with density rho and viscosity mu between two horizontal parallel plates. So, coming to this problem first, two viscous incompressible immiscible fluids of density rho, but different viscosities. Viscosity of the lower fluid is given as mu 1 and that of the upper fluid is mu 2, flow in separate layers between two stationary parallel plates of distance 2h apart. Thickness of each layer is identical and their interface is flat. The flow is driven by a constant favorable pressure gradient dP dx. You have to derive expression for the velocity profiles in the fluid layers. You can assume flow to be steady and the plates to be infinitely large width. So, coming to the description of the problem, it is given there is a distance between the two plates 2h, density is rho, dynamic viscosity of the lower fluid is mu 1 and that of upper fluid is mu 2. So, you have to derive the velocity profile for two different layers of fluids. So, for that you have to start from the Navier-Stokes equation in the Cartesian rectangular coordinate system. So, if you remember that the equation for that simplifies to d2u dy2 1 by mu dP dx. This is under the condition that already one is the for incompressible flow, steady flow and fully developed flow. So, for this case we divide the entire domain into two regions, one is minus h 0 y 0 and another is the 0 . So, let us consider the velocity profile for the lower is u 1 and that of upper layer is u 2. So, for minus h we can simply write the governing equation as 1 by mu 1 dP dx. Now, if we integrate this equation, we can simply get the velocity profile as 1 by twice mu1 dp dx y square plus c1 y plus c2. So, before coming to the boundary condition, let us have a look how the velocity profile becomes for the upper layer of fluid. Now, for the upper layer of fluids, that is the domain is from 0 to h, the governing differential equation becomes u2 1 by mu2 dp dx. So, again if we integrate this, we will get u2 equals to 1 by 2 mu2 dp dx y square plus c3 y plus c4. So, there are 4 constant integration constant c1, c2, c3 and c4. Now, your objective to find these 4 constant from the boundary conditions. So, now if you consider the what are those boundary conditions? First boundary conditions, if we consider the lower plate, at the lower plate means at y equals to minus h, from the no slip boundary conditions the velocity u1 will be 0. So, we can simply write at y equals to minus h u1 equals to 0. Similarly, if you consider the upper plate here at y equals to plus h, again similarly from no slip boundary conditions u2 will be 0. Now, what is about the interface? Now, interface if we write simply at y equals to 0, it is clearly mentioned in the problem that the thickness of each fluid layer is identical, and that is why you can simply write at y equals to 0. What is the relation between velocity of lower layer and upper layer? There is a continuity in velocity across the 2 layer of fluids. So, we can simply write at y equals to 0 u1 is same as that of u2. Similarly, at y equals to 0, one more boundary condition is needed, and we can simply write mu1 du1 dy is simply same as mu2 du2 dy. This is nothing the continuity in shear stress. So, we can simply write first and second boundary condition are the no slip boundary conditions, and third or fourth boundary condition at the interface there is a continuity in velocity and there is a continuity in shear stress. So, now I leave it an exercise by putting these 4 boundary conditions on the 2 velocity profiles. One is this u1, another is here u2. Just we find the values of c1, c2, c3 and c4, and you ultimately find what is the u1 and u2 and try to plot u1 and u2 and find what is the velocity gradient at the interface. Now, coming to the second problem, consider steady fully developed laminar flow of oil with density rho and viscosity mu between 2 horizontal parallel plates h distance apart. The upper plate moves to the right, that is the positive x directions with a uniform speed capital U, while the lower one is kept stationary. A constant pressure gradient dP dx drives the flow. Now, your first objective to derive an expression for the velocity profile, then determine the location where the velocity is maximum or minimum, and lastly you have to find the magnitude of the pressure gradient for which the net flow rate across any section is 0. As mentioned in the today's first lecture, this is combined Couette and Poiseuille flow. So, now if we draw the flow geometry, this is the lower plate which is stationary, and this is the upper plate. This is moving with a velocity capital U that is given in the problem. The distance between two plates is given as capital H, and it mentions that a constant pressure gradient dP dx that drives the flow. So, now if we give this is x coordinate, the governing differential equation will be similar to earlier one, that is for plane Poiseuille flow. So, we can simply write d2u dy2 that is 1 by mu dP dx. Now, if we integrate this, we can simply get u equals to 1 by mu dP dx y square plus c1 y plus c2. So, here the boundary condition will be different from the plane Poiseuille flow. What are those boundary conditions? First boundary conditions, at y equals to 0, from the no slip boundary conditions velocity is 0, and at y equals to capital H, u is capital U. So, from the first boundary conditions, if we put on the velocity profile, C2 will be 0. Now, from the second boundary conditions, u equals to capital U, that is 1 by 2 mu dP dx capital H square plus C1 capital H, from where you can simply get C1 as capital U by H minus 1 by 2 mu dP dx H. So, if you substitute the value of C1 in the velocity profile, you will get U as U small y by H minus 1 by 2 mu dP dx H y plus 1 by 2 mu dP dx y square. If we arrange this little bit, we will get 1 by 2 mu, let us have minus dP dx. Now, if we write y by h, 1 minus y by h, here you write capital U. So, 1 by capital U here and H square. Fine. So, let us consider this term as one parameter p. So, you can write u as capital U y by h plus p u y by h 1 minus y by h, where the parameter p is a square by 2 mu minus dp dx. So, this is the velocity profile which combines to first term due to the shear, that means the upper plate is moving with a uniform velocity, or the second term is due to the Poisson flow, that is due to pressure gradients. Now, second objective of this problem is to get the location for the where the velocity is either maximum or minimum, and as you know, for getting maximum or minimum velocity, the first the velocity profile should have inflection. That means, if you write in terms of equation del u del y, del u del y should be 0. The point where the velocity is either maximum or minimum, the del u del y will be 0. So, now if we differentiate this, we will get a value of y for which the velocity is either maximum or minimum. So, just if we carry out this, just u by h plus p u by h 1 minus y by 2h. So, this quantity will be 0, from where you can simply get the value of y for which the velocity is either maximum or minimum. So, try to find out what is the value of y for which the velocity is either maximum or minimum. So, now question comes, how to check whether the velocity is maximum or minimum. So, for that, here you have to carefully look about the parameter, non-dimensional parameter p. So, first consider two different cases separately. First one is the p is greater than 0, that is the p is greater than 0 means the dp dx is less than 0, that means a favorable pressure gradient. And for different range of p, for example, let us say for 0 to 1, first try to assess whether there is a velocity is maximum velocity occurs within the flow domain or not. Then try to assess for p equals to 0 whether maximum velocity occurs or not. Then for p greater than 1, try to assess the same. This is the case 1, and for case 2, try to assess for p less than 0, that means dp dx is greater than 0, that means for adverse pressure gradient. Then similar to previous one, try to assess what happens for different range of pressure. Means the one is p is exactly equals to -1, and another is the p is less than -1, and another is the from 0 to -1. And after having this, just try to find out so for this range. Obviously, if you carefully look, there is no maximum velocity will not occur within the domain, there will be minimum velocity, and try to assess for what values of p or range of p this minimum velocity occurs. I will leave it exercise both the cases to try to assess from getting value of y max or y mean. And next, last part of this problem, find the magnitude of the pressure gradient for which the net flow rate across any section is 0. And for that you first find out the velocity profile, and the at any section the volume flow rate is just u. If you consider unit width, then 0 to h. The first substitute this u from the velocity profile you obtain, then you will get some values in terms of the pressure gradient and the velocity of the upper plate, and put that equals to 0. That means the net volume flow rate at across any cross section is 0, and from which you find the pressure gradient in terms of the velocity of the upper plate, obviously the viscosity of the fluid, and the distance of separations. I also leave this as an exercise problem. Just find out the expression for pressure gradient for which the net volume flow rate across any section is 0. So, then I will have handed over to Professor Chakraborty for question answer session. One two zero zero.
Hello. Hello.
RCID 1200.
Hello. Good afternoon, sir.
Good
Sir, my
afternoon.
question is that what are the limitations of boundary layer theory?
Well, I mean this was not taught by me, but I will be answering this question because Professor Ghosmolik is not present in this session. It is not a question of limitation. I mean there are certain assumptions based on which the boundary layer theory is developed. One of the most important assumptions is that the Reynolds number is large. So, for low Reynolds number you cannot use the boundary layer theory, because in the boundary layer theory you are assuming that the characteristic boundary layer thickness delta is much less than the characteristic length scale L. So, if delta is not much less than L, then this is not valid. So, you cannot use the boundary layer theory when Reynolds number is small, although the concept of boundary layer is there. Remember that boundary layer concept and boundary layer theory, they are two different things. Concept of boundary layer is a layer close to the wall within which the viscous effects are felt. So, that layer may be thin or thick, but boundary layer theory is a theory which simplifies the Navier-Stokes equations based on the fact that the thickness of the boundary layer is small as compared to the length scale. So, one of the major assumptions is that the boundary layer one of the major assumptions behind the boundary layer theory is the Reynolds number is large, and the second important assumption is that there is no boundary layer separation. That means there is no flow separation and there is no reverse flow. So, there are two important major assumptions based on which you can apply the boundary layer theory. One is the Reynolds number is large, and the second, there is no boundary layer separation. One 1178.
Hello sir, am I audible?
You are not audible.
Hello sir, am I
Yeah,
audible?
yeah.
My first question is, on which factor entrance length is depends before flow becomes fully developed? Is it depends on boundary layer or any other parameters?
The entrance length, it is a function of the diameter of the pipe. So, how do you find out what is entrance length? So, let me give you a quick way of assessing it. So, let us say there are two plates, two parallel plates like this, and you have the expression delta by L or delta by x is of the order of Reynolds number to the power minus half typically. So, when there will be fully developed flow, when delta becomes equal to, this is delta, the boundary layer thickness, when delta becomes equal to the radius of the pipe, that is the entire pipe feels the effect of the wall, when delta is equal to r, L is of the order of, x is of the order of L entrance, which is called the entrance length. So, we can write R by L entrance is of the order of Reynolds number based on the entrance length to the power minus half. From here you can find out what is the order of the entrance length in terms of the radius of the pipe. So, the radius of the pipe or the diameter of the pipe, typically from that you can find out what is the entrance length, pipe or channel, whatever. Okay, next question. 1059. You are not audible. Sorry, you are not audible. Sorry, you are not audible.
Hello?
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 Yeah?
Good
1
evening,
2 2
sir.
3, yeah.
My question is, are the Pauli flow and Corti flow simultaneously exist in it or not?
What is your question? I do not understand. Oh, do Poiseuille flow
So
and
are the
Couette flow simultaneously exist or not?
exist in a flow or not?
Yes, in a flow there can be, see what are the mechanisms of actuating a flow. You can have a pressure gradient and you can have a shear. So, if you have a combination of shear and pressure gradient that is driving a flow, that is called as Couette Poiseuille flow. So, it is possible that there is shear that is driving the flow plus there is a pressure gradient, that is that there is a difference in pressure between the inlet and exit of the channel. So, that makes the flow combined Couette and Poiseuille. One two two one.
Hello, sir.
Hello,
Good evening, sir.
good evening.
What is the practical applications of Van Karman momentum integral equation?
See again, although I have not taught this particular portion, but I can give you the answer. See, to calculate
Sir?
the what is important in engineering. In engineering it is important to calculate the wall shear stress, because that effectively gives you the drag coefficient. So, when you are calculating the wall shear stress, you require an information of the velocity profile, but even if you do not have the correct information of the velocity profile, you can use integrals of the velocity profile to calculate the wall shear stress in an approximate sense. So, to calculate, so momentum integral equation gives you an approximate yet very accurate method of calculating the wall shear stress without correct knowledge of the velocity profile, provided the boundary conditions are appropriately satisfied. Now, I would request all of you to restrict your question to dynamics of viscous flows, only internal flows. What I have taught, the other questions, that is questions related to boundary layer theory, will be addressed by Professor Ghosh Maulik tomorrow.
1131.
1131.
Hello.
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 Good evening, sir.
Good evening.
Hello. Good evening, sir.
Good evening.
I would like to ask the three questions to you. The first one is, how the term dou 2u by dou x square vanishes by in the Prandtler's bond layer approximations from the Navier-Stokes equations. The second
Okay,
one
okay,
is
one
what are
by
the
one.
similarity transformations?
I cannot remember all the 3 questions. So one by one, one by
Okay.
one. Again, this was not taught by me, but I will try to explain. See, look into this workout very carefully. You have 2 terms, 2 viscous terms. We have 2 viscous terms, mu del 2 u del x 2, mu del 2 u del y 2. This is of the order of mu u infinity by L square, because think of flow over a flat plate, the order of magnitude of x is L and the order of magnitude of y is delta and free stream velocity is u infinity. So, this term is of the order of mu in u infinity by L square and this term is of the order of mu u infinity by delta square. Okay. Because delta is much less than L, this is the one of the important assumptions for boundary layer theory, and this is valid when Reynolds number is large, boundary layer theory assumption. So, if delta is much less than L, mu u infinity by delta square is much greater, this is much greater than this one, mu u infinity by L square. That means this term significantly overweighs this term in the boundary layer. That is why we keep this term and not this term in the boundary layer equation.
Hello.
Yes.
Okay, sir. Second question.
Yes.
What are the similarity transformations and when to use and how to use that?
See, similarities,
Transforming partial,
similarity
transforming partial
transformation,
differential equations.
similarity transformations are like transformations when there is a parameter, there is a similarity parameter that exists. I will give you an example. So, let us consider the boundary layer. If you plot the velocity profiles, you have u by u infinity. So, u as a function of y, so this is y. So, at different y you have different velocity profiles. So, velocity profiles at different x are different, but if you non-dimensionalize, if you plot u by u infinity as a function of y by delta, then you will get a unique velocity profile. So, you can write, so all these velocity profiles are self similar. This, for example, this velocity profile is just a stretched version of this velocity profile. So, you can write u by u infinity as a single function of y by delta. U as a function of y is different for different x, but u by u infinity as a function of y by delta is unique. So, this function of y by delta we call this as eta. So, when there is such a similarity parameter, we can replace the function, remember that delta is a function of x. So, eta you can write as y into some function of x, where this gx is like 1 by delta. So, it is possible, so this is a special case of separation of variables. It is possible to write a variable eta which is y into a function of x. and this transforms the partial differential equation governing the boundary layer velocity variation into ordinary differential equation. I hope this explanation is clear to you. You are not audible. One 1117.
Good evening.
Good
Suman
evening.
Sir.
Good evening.
My question is, in the previous lecture, you have explained about the factors which make the irrotational flow to rotational flow.
Yes.
One factor was shock wave.
Yes.
My
Yes.
question is, what are the shock waves, how they are formed, and where they are formed?
Now shock waves are formed in compressible flow where there is abrupt discontinuity of properties. So in supersonic flow typically you will have shock wave where in the upstream section there is supersonic flow and in the downstream section there is subsonic flow. So what happens actually is that the source of disturbance, so if you consider the Mach number is u by c. So if Mach number is greater than 1, then the source of disturbance speed u is greater than the sonic speed. That means the source of disturbance moves at a speed faster than the sonic speed. Now because of this what happens, there is accumulation of disturbance at certain locations. Disturbance cannot be diffused instantaneously. So this accumulation of disturbance is released at certain locations in the form of shock. So that is the physical mechanism of shock in a compressible flow. One 1097.
Good evening, sir.
Good evening.
The question is about external flow. Can we apply the similar analysis which we did for flat plate to a flow over a aerofoil?
Yes, I mean just the geometry will be different. Instead of a flat plate it will be a curved surface. So but similar considerations can be applied, but you have to be careful about the flow separation, because if boundary layer separation occurs you can no more use the boundary layer theory. So you have to understand that in the, so if this is an aerofoil, just I am trying to draw a sketch. If this is an aerofoil, okay, I am trying to draw the sketch, but
Sketch is not visible.
yeah, now I hope it is visible. So
Yes, it's visible, sir.
so you can use the boundary layer theory with local coordinates x and y like this. So locally your x will change and y will change. Flat plate, x and y, x is along the plate and y is perpendicular to the plate, and because along the plate direction is same, therefore x y directions are the same, but x and y are called as boundary layer coordinates and they are fitted to the body, fitted to the shape of the body. So you can see that for a curved surface, not just an aerofoil but any curved surface, x and y will vary continuously, that is the first change. And the second change is because of the curvature there can be an adverse pressure gradient which may lead to boundary layer separation, and then boundary layer theory can no more be used. Okay, next question. 1305.
Hello.
Yes,
Good evening, sir.
good evening.
Sir, yesterday you told that the Navier-Stokes equation you have taken one example of the circular pipe. In that case, you said that the mass flow rate just have to maintain
Yes,
in flow through pipe.
yes,
But in the circular pipe, whatever that the velocity at the center, it will be the increasing,
yes,
and the mass flow rate, it is nothing but the rho a v.
No, 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 not rho A V, rho A V average. Rho A V average, as I told you, so these are certain misconceptions, right. Mass flow rate is rho A V true, but not local V, it is rho A into V average, and V average is the integral of the velocity profile over the cross section divided by the area of cross section, and the integral of the velocity profile depends on the velocity distribution. Okay. So, when you write rho A V, this is not local V, this is rho A V average, where V average is defined in this way. Okay.
Next question.
Next question. Yes.
Hello, sir.
Hello.
Sir, why we are studying? Hello, sir.
Yes.
Sir, my question is why we are studying boundary layer concept. Please explain it with certain practical examples.
Okay. So, let us say that you want to study flow past an aircraft, okay, or flow past the body of a ship. Now, depending on the relative velocity between the fluid and the solid, there will be a Reynolds number, and you can, based on the Reynolds number, you can define a thickness within which viscous effects are felt. So, you can demarcate the or divide the flow region into two parts. One part is close to the wall where the viscous effects are felt, you have to write the equations with viscous terms, and outside that region there is no need to solve the full equations with the viscous terms. You can neglect the viscous terms and solve the equation without viscous effects or dynamics of inviscid flows. Mathematically it is much more simpler to solve the dynamics of inviscid flows than to solve the dynamics of viscous flows. So, boundary layer theory, what it does, it decomposes the flow region into two parts, and it allows you, it enforces that you apply the viscous flow considerations only within a thick layer, only within a thin layer, and based on this theory the next important application is that you can very elegantly calculate the drag force without solving the full Navier-Stokes equation for the entire domain. So, because you can very easily calculate the drag force, you can design the ship or the aircraft based on that drag force calculation. Hello,
good afternoon, sir.
good afternoon.
Sir, my question is, what is the approach of analyzing the flow between two plates which are inclined at some angle to each other?
Okay, so if you have I mean, first of all it will no more be parallel flow, and I mean this kind of application is there when the angle of inclination between the two plates, of course it is restricted within a certain limit, and this is there in slider bearing. With certain approximations known as lubrication approximations, you can solve this problem analytically in a two dimensional form with the help of the two components of the Navier-Stokes equation. It is beyond the scope of this course or this question answer session to work out the full details, but I am just giving you an outline. For full details please refer to any textbook on fluid mechanics that contains the description of lubrication theory.
Okay, thank you.
Okay. One three three
Hello.
six.
Good evening, sir.
Good evening.
Hello.
Yeah, hello.
Sir, my question is, in the last class you have mentioned about unidirectional flow and one dimensional flow.
Yes.
They have some kind of difference. So can you elaborate about it?
So, one dimensional flow is like you have only one velocity component u, it does not tell you that u depends on what, it tells just there is only one velocity component. Unidirectional flow says that you have one velocity component, but that velocity component may depend on some another coordinate y.
So can we visualize it? Means suppose a flow is there, so can we be able to know that whether it will be unidirectional flow
Yes,
or
yes,
one
I mean
directional flow?
you can get the velocity profile by many methods. You can inject a dye, or you can put tracer particles in the flow and illuminate the flow field by a laser light and visualize the flow. That is commonly done in particle image velocimetry or PIV. So it is possible to get a visual description of the velocity profile, and from that you can conclude whether it is unidirectional or not.
Sir, my next question is, when you are deriving Navier-Stokes equation,
Hmm.
then you have considered a particle and applied the Newton's laws, means all the laws of Newton
Not
directly.
particle,
So
not particle, these are not particles, these are fluid elements. There is a difference between particle and a fluid element. So if we have considered this fluid element, we have considered that there is change within the fluid element at a given instant of time, plus there is a net flow term, outflow minus inflow term. The flow takes place across the faces. So when you are considering,
sir, which
you please allow me to complete my explanation. I have understood your question, and then if you have any question remaining you can tell me. So the total change is sum total of the change at a given location due to change in time plus outflow minus inflow across these phases of the control volume, and this is the total change ddt. So in other words, this is nothing but the Reynolds transport theorem. So the rate of change across the system of identified mass, which is a fluid element or which you are considering as a particle or system or whatever, this is sum total of two things. One is the change within the control volume due to change in time plus outflow minus inflow. So what we have written is same as what we would have otherwise written with an arbitrary control volume using the Reynolds transport theorem, but we have written that in a more informal way which looks like the description, the well known school level description of the Newton's second law. This is just for the convenience of the beginners who are not so familiar with the Reynolds transport theorem, but they know that how to apply Newton's second law for a system.
that means, sir, we can utilize this method in place of Reynolds theorem in
No,
other
this is
problem
Reynolds
solving?
transport theorem, that is what I have precisely explained. See what I have the equation that I have considered, the right hand side, the two terms together, this is nothing but the right hand side of the Reynolds transport theorem. Only formally I have not told that it is a Reynolds transport theorem, but it contains all the terms which are there in the Reynolds transport theorem.
Okay, sir, thank you.
Okay. One 1002. You are not audible. Sorry, you are not audible. Sorry, you are not audible. One 255.
Good evening, Professor.
Good evening.
Good evening, sir.
Good evening.
My question is, I have a few questions here. From Viscous flow in velocity profile, sir. In velocity profile, because of change in that angle, we are determining some angle is there, no? Because of that change in angle, there will be small changes in area also will be there.
What angle and what area? I cannot understand your question. You please elaborate it. Angle, what angle? Angle between what?
It is the angle between delta and distance.
Angle between?
X and y axis, sir.
Huh? Angle between x and y axis is 90 degree.
No, not like that. Between in the velocity profile, we are getting some curves. Curve is there, no, sir.
Velocity profile is a curve. So
profile curve is there.
Anyway, you frame your problem
Yes,
correctly,
the flow is there, no?
we will get back to you. You please frame your question correctly because it is not comprehensible. We go to a next 1312.
Sir, good afternoon, sir.
Good afternoon.
Sir, I have one clarification on that second tutorial problem. In
Okay.
that problem, that equation u is equal to 1 by mu dp by dx into y square plus c1y plus c2.
Yes.
The first boundary condition apply that y is equal to 0, then u is equal to 0.
Yes.
Then the c2 value will be 0. But the second boundary condition will be up. That sir told us u is equal to 1 by 2 mu into dp by dx capital H square plus c1h. Sir, how to get come that 1 by 2 mu, sir?
Integral of y dy is y square by 2. So,
Sir?
See, let me write it like this. I mean whether 2 mu or mu that you check, but it is just a matter of this, like du d2u dy2 is sum a. So, du dy is equal to ay plus c1. So, u is equal to ay square by 2 plus c1y plus c2, right. So, that is the generic integration, and then this c1 c2 you have couple of these values, one c1 c2 for one layer, another c2 c3 c4 for another layer. You have 4 unknown coefficients and 4 boundary conditions. So, you will get 4 equations with 4 unknowns c1 c2 c3 and c4. From that you can evaluate. Okay, thank you. Next question 1107.
Hello.
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 Sir, am I audible?
Yes, you are audible, but I cannot see you.
Sir, I want to ask that do there is any general accepted theory for turbulent boundary layer thickness?
General
Or
accepted.
laminar boundary layer thickness?
All theories are accepted. I mean,
Actually, for I want to ask that for laminar boundary layer thickness, for 99% of free stream velocity,
yes,
we take the thickness. But in case of turbulent flow, what do we take?
same 99% of average free stream velocity instead of the 99% of u average, u infinity
Even
average.
for boundary, for
Yes.
both laminar and turbulent boundary layer thickness.
Yes, boundary layer, what is the boundary layer? See, typically boundary layer thickness is infinity. If you ask some mathematician, a mathematician will say that I do not understand boundary layer, it extends up to infinity. As engineers we know that there is a finite region which we call as infinity. What is that region? That region is where the velocity is roughly 99% of the free stream velocity. So, 99% is as good as if you have reached the free stream.
Means for both the cases laminar and turbulent
Yes, it
boundary
has,
layer thickness,
yes,
99% is the accepted
yes,
thickness
yes,
like
yes,
this.
yes, 99%. One 1043.
Namaste, sir.
Namaste.
Sir, the question was regarding the Hagen-Poiseuille flow explained by you today morning, sir.
Yes.
Sir, how do we interrelate the effect of aging with this all equations that we learned like for fully developed laminar flow profile as well as the Hagen-Poiseuille's equation? As such, while
what
we
is
are
aging? What is aging?
Sir, when we are developing designing a pipeline network,
yes,
we calculate the values of discharge and velocity and pressure for different outlet points.
Yes.
Now, if the system is already established, let us say for 15 years or 12 years or 20 years.
Okay.
So if we want to refurbish,
you
want
mean
to refurbish the entire system.
You may surface effect. You mean surface effect.
Yes, sir. Yes, sir.
So, first and foremost important concept is that for laminar fully developed flow, the velocity, the friction factor is independent of the surface roughness, it is only a function of the Reynolds number. This is the first and foremost important concept. Why it is so? Because even if there are roughness elements, the fluid is moving in a nice regular orderly manner. We will discuss about turbulent flow tomorrow, and there we will discuss what is the distinction between this kind of flow that we discussed today and the turbulent flow. But just to be precise, there is regular orderly motion of fluid elements, and that means the roughness effect does not perturb the flow, and that means the effect of the roughness or effect of the wall undulations, I mean local fluctuations in the wall profile, I mean after aging or before aging, whatever, that does not come into the picture when you are considering a fully developed laminar flow. So, friction factor is a function of Reynolds number only. For turbulent flow, however, it depends on the roughness of the pipe, and that will be discussed by Professor Shom when we will be talking about flow through pipes.
Thank you, sir.
Okay. One two 5 2.
Good evening, sir.
Good evening.
Yes, the deformation of fully developed velocity profile was mentioned with regard to a parallel plate.
Yes.
The but I want to know about that, whether this concept can be used for converging or diverging plates also.
Okay, so you have to consider one important thing. Let me draw a sketch to explain this. So, let us take a converging section for example. Okay. So, in the converging section, if you draw the velocity profile, so let us draw the velocity profile. At the next section, what will happen? Because the flow rate is conserved, because the area has reduced, the velocity should increase to make up for the loss, the reduction in area. So, you will have the flow velocity as a function of u as a function of x. Because u will be a function of x, v will not be equal to 0. So, instead of having a unidirectional flow, you will also have the v component. Okay, so similar concept, same equations you can use, but the equations will involve more terms because it will become a 2-dimensional flow. Remember that in the velocity profile, we only draw one component of the velocity, it does not tell that the other component is absent, the other component may be very much present.
Sir,
1177.
Good evening, sir.
Good evening.
Is it audible?
Yes, you are audible.
Good evening, sir.
Good evening.
In the cavity flow derivation, we have the boundary condition y is equal to 0 and u is equal to 0. And second boundary condition y is equal to h and u is equal to u1.
Yes.
After that, we come to the permittive flow. We put the u is equal to u1 and u is equal to u2. Here, what is the value for y, sir?
What is that question that you have asked? I cannot understand.
Sir, in the boundary condition 2, y is equal to h, sir.
At y, so there are two boundary conditions, at y equal to 0, u equal to 0, and at y equal to h, u equal to u1. So that is the Couette flow problem.
Yes, sir.
There
After
are
that
two.
we come to the combined.
Oh, combined. Combined Poiseuille and Couette flow. So there also at y equal to 0, u equal to 0, and at y equal to h, u is equal to u1. That boundary condition does not change, whether, because irrespective of whether it is Couette or combined Couette Poiseuille, because pure Couette or Couette Poiseuille, it depends on whether there is a pressure gradient or not, but effect of a pressure gradient does not affect the boundary condition at the bottom plate and the top plate.
Good evening, sir.
Good evening.
Sir, yesterday you taught about that entrance region and fully developed region, sir.
Yes.
How you find out that up to this is the entrance region, then how I can differentiate that from fully developed region, sir? Is there
I
any?
mean, this question I have answered in this particular session only. In this particular session, I gave an answer to this question, but I can repeat that question, that from boundary layer analysis you can predict that at what length the boundary layer thickness will be equal to the radius of the pipe, and that length is the entrance length. So, that length is a function of the radius of the pipe.
Thank you, sir.
1316.
Hello.
Hello.
Good evening, sir.
Good evening.
My question is from potential flow field.
Yes.
In the flow field, suppose U is given, this one component of this velocity is given as function of x and y. Another component V also is given as a function of x and y.
Yes.
Now at that point, of course, we have the stream functions available. So in terms of stream function, it can be the same U can be expressed, and again the same V also can be expressed in terms of a stream function.
Yes.
Now, if we integrate that stream function,
yes,
related to the U, we are getting some expression for the
yes,
stream function.
yes,
a certain constant.
Okay. Yes.
And another side again, if you integrate the V side,
yes,
we are getting another stream function with another constant, say
yes,
C2.
yes.
So, sir, what will be the actual stream function for that particular
No,
point?
they are the same.
where we
They
have
are the same. In fact, you find out the constants. The constants, remember one very important thing, many books do it wrongly. Please do not read bad quality books which give those as constants. Those are actually functions of x and y, because when you write u equal to del psi del y, so then psi is equal to integral of u dy plus a function of x, not a constant. Why this is a function of x? Because with respect to derivative or integral with respect to y, function of x is like a constant. Similarly, v is equal to minus del psi del x, this implies psi is equal to minus integral v dx plus a function of y. So now these are same, the stream function cannot be different based on u and v. So because they are the same, by comparing these two expressions you can calculate, you can determine f and g, but it is not different stream functions, it is the same stream function.
So how can we compare and get this x, y separate?
I have worked out a problem, I have worked out a problem exactly on this, exactly this one I have worked out in my lecture. So please rerun it, rerun the video if you were absent in the lecture by that time. In the tutorial problem also it has been given. So many of you have not attended the lectures and have not participated well in solving the tutorial problems. So please refer to those, that is what is my earnest request, that do not just ask question arbitrarily without going into those. If you see that if you have gone through the lectures and have gone through the tutorials, many of these trivial doubts will be clarified. So please go through that. After that, even after that, if there is any doubt, we will be happy to answer.
Thank you, sir.
Okay. 1263.
Good evening, sir.
Good evening.
I have two questions, sir. First question, sir, regarding boundary layer, we can classify the boundary layer zones into two types, laminar boundary layer and turbulent boundary layer.
Yes.
My question is it necessary to go for transitional boundary layer?
See,
my second question related.
Okay, let me first answer your first question, because it is difficult for me to remember two questions. Okay. So when you have a boundary layer transition from laminar to turbulent, it does not occur abruptly. So there is a region over which there is a transition from the laminar boundary layer to the turbulent boundary layer, and but analysis over the transition region is a very complicated region which has not yet been fully understood theoretically by experts, by fluid mechanics analysts. So it is a mystery really that what happens mathematically in the transition region, and that is still an active area of research. Next question.
Yes, sir. My next question regarding to thin film flow.
Yes.
I agree that thin film is proportional to mass density, angle of inclination, right? Is it not affected by the surface tension of the fluid, since the surface is dealing with the thin film at the top?
See,
is it not affected, sir?
See, the flow, the thin film flow, it depends on the film thickness. See, the problems that we have solved for a thickness h which is not comparable, which is thin as compared to the macroscopic scale, but much thicker as compared to the nanoscopic or microscopic scale. So if you come your thickness of the film which is nanoscopic or microscopic scale, then the surface tension forces become important, and the contact angle at the wall will between the film and the wall, that will be very important. So based on that, I mean between the liquid and the wall material will be important, and based on that, like if you have a hydrophobic wall or a hydrophilic wall, the way in which the liquid will be covering the surface, that will be different. So you are correct, it will depend on the surface tension, but it depends on the scale. So we have not considered H to be sufficiently small so that surface tension forces come into the picture. (1064).
Hello, my first question is,
yes,
how the presence of shock waves, hello,
yes, you are audible.
नहीं symbol आ रहा है.
Yes.
How the presence of shock waves act as a discontinuity and make the irrotational flow a rotational flow.
Okay, let me answer you this question. See, across the shock wave there is a release of accumulation of disturbance. So because the disturbances are released, there is a discontinuity in the Mach number. From supersonic flow it becomes subsonic flow, and this gives rise to discontinuities in properties, and because of the discontinuities in properties there are strong velocity gradients also, and because of these strong velocity gradients an irrotational flow can become a rotational one.
My second question is, in the absence of the body couples, the tau ij is taken as tau ji.
Yes.
What is this body couple concept? Please elaborate.
See, body couples means that just like body forces, there can be couples. You can understand couple. Couple is like you have if you have two forces which are equal and opposite, they actually form a moment. So this forms a moment M, which is called as the couple moment. So if in just like body force, if such couples are present within the volume of a fluid, that is called as body couple. So normally fluids will not be able to sustain these body couples, but if there are particulate matters within the fluid, that may sustain these body couples. So if these body couples are there, then tau ij is equal to tau ji plus some correction term which is a function of the body couple. If the body couple is not there, then tau ji and tau ij are the same. Okay, we will take one last question before we conclude this session today. 1256.
Hello.
Hello.
Very good evening, sir.
Very good evening.
Hello, very good evening, sir.
Yeah, good evening.
Sir, my question is, if we, for example, if we take a centrifugal pump transferring high viscous fluid,
yes,
in this case boundary layer is considered or not? This is my question, sir.
See, you will be taught about fluid machines by Professor Som, and there this issue will be discussed. Like it depends like how thick or thin the boundary layer is, it depends on the Reynolds number. So if the Reynolds number is very large, the boundary layer thickness is very small. So now whether the boundary layer effects are taken or not in analyzing a fluid machine, it depends on several parameters, but one of the most important parameters is the Reynolds number.
Okay sir, thank you sir.
So we will take 2 more questions, we will take 2 more questions today. There are actually many questions and we will take 2 more questions. 1128.
Hello sir.
Hello.
Am I audible?
Yes, you are audible.
Hello sir.
Hello.
Sir, I wanted to ask the question that if the heat station whether it's going to affect boundary thickness.
You are not audible. Could you repeat? Your voice is actually getting distorted. I am not able to listen to you. Sorry, you are not audible. We will go to a different question. 1330.
Sir.
Good afternoon.
Sir, my question is about the Navier-Stokes equation.
Yes.
How this Navier-Stokes equation is classified, and what is the procedure to classify this Navier-Stokes equation?
There is no classification of Navier-Stokes equation. Navier-Stokes equation is Navier-Stokes equation. There is no classification, there is no basis for classification. So if you have heard about classification of Navier-Stokes equation from some source, that is not correct. We do not classify Navier-Stokes equation, because Navier-Stokes equation is based on certain assumptions. If those assumptions are valid, Navier-Stokes equation is valid. So what you have possibly heard of is a simplification of the Navier-Stokes equation based on certain restricted places, but that is not classification. So if you are talking about classification based on the nature of the partial differential equation, are you talking about that? Are you talking about the classification of Navier-Stokes equation based on its mathematical characteristic, parabolic, elliptic, hyperbolic, are you meaning that? Well, I am not able to get the feedback from you, but
yes sir.
But you can have classification of the partial differential, I mean in a mathematical term. So if you talk about Navier-Stokes equation in a mathematical term, it can have 3 types of three types of classifications: parabolic, elliptic and hyperbolic. These depend on various characteristics. I mean, in this short discussion it is impossible to discuss about it in length. So I would request you to look into my NPTEL lectures on computational fluid dynamics, my NPTEL lectures on CFD, where I have discussed in details the classification of partial differential equations, parabolic, elliptic and hyperbolic equations. Okay.
Sir,
so
is it dependent on the values of Mach number?
I mean if the compressibility effect is important, that is, if you are talking about hyperbolic equations, then it is a function of the Mach number, if you are talking about the hyperbolic equations.
Sir, there is another question from our side. Sir, please explain the adverse pressure gradient and boundary layer separation.
Okay, this is a topic that will be taken up by Professor Ghosh Maulik, but I am just giving you an overview, so that when Professor Ghosh Maulik will explain, it will be easy for you to understand. Let us say you have flow past a circular cylinder. This is a part of a cylinder, I am just drawn a surface. If you consider a streamline which is there far away from the cylinder, then over this region what is happening, the area of cross section, the area of flow available, that is continuously decreasing. So the fluid is accelerating. But if you consider the section beyond this, then the area is continuously expanding. Because of that, the fluid is decelerating. So the fluid is decelerating and then the wall is trying to aid that deceleration effect. The wall is trying to slow the fluid down further, and then because here also the wall is trying to slow down the fluid, but because the fluid is accelerating, so what is happening here, the fluid is accelerating because the pressure gradient dp dx is less than 0. It is called as favorable pressure gradient or adverse pressure gradient, favorable pressure gradient, and this is in this region you have dp dx greater than 0, this is called as adverse pressure gradient. So in the adverse pressure gradient what is happening, the fluid is encountering more and more pressure as it is moving along x direction. So when the fluid is having encountering more and more pressure, it is actually slowing down. So here the pressure gradient is driving the flow, that is why the fluid is accelerating. Here the fluid is decelerating. On the top of that, if there is a wall effect that is trying to slow the fluid down, then there can be a back flow. So instead of the fluid flowing in the forward direction close to the wall, the fluid can start moving back, and because the boundary layer is defined based on a monotonic increase in the velocity, because of the back flow we will assume. So let us say that there is a back flow. Let me try to draw a schematic of the velocity profile. So if there is a back flow, the velocity profile may be something like this. So the point of location of 0 velocity has got as if shifted from the wall to here, in a sense that beyond this there is a monotonic increase in velocity. Earlier from the wall there is a monotonic increase in velocity. Now the monotonic increase in velocity is from here to further outwards. So what we can say is that as if the boundary layer has got detached, and the detached boundary layer can be found out by considering the locus of all such points. So let me try to physically explain what is happening. Let us say that you are moving slowly. If you are moving slowly, if somebody kicks you at the back, you will tend to have a backward motion, but I mean kicks you in the backward direction, not kicks you in the forward direction. So you are moving slowly and somebody is kicking you in the backward direction, you will have a tendency to move backwards. But if you are running in the forward direction and somebody is kicking you in the back, still because of your momentum you may be able to sustain your forward direction, forward motion. That is what is happening in this region. But over this region in the adverse pressure gradient, because of slow momentum of the fluid within the boundary layer, because of deceleration that is imposed by the outer stream, the resistance of the wall may make sure that there is a reverse flow, and that leads to boundary layer separation, and this is triggered by adverse pressure gradient from the outside of the boundary layer, imposed from outside of the boundary layer. Okay, we will take one more question maybe. Yes, last question. One 1059. You are not audible. We will go to a different question. 1207.
Hello, good afternoon, sir.
Yes, good afternoon.
Sir, my question is there a velocity distribution? Is that different for the different flows, like laminar flow and the turbulent flow? There is a two flows. Is that different for the velocity distribution? Is that different for the two flows? If we going through circular pipe or maybe plate?
I cannot really get your question. What is what is?
Velocity,
I cannot get your
velocity
question.
distribution.
I cannot get your question.
Velocity.
It's not audible properly. We will go to a different question. 1241.
Hello.
Yes.
Good afternoon, sir.
Good afternoon.
Sir, my question is that what are the different factors affecting on boundary layer conditions and boundary layer separation? Is this physically concept or hypothetically concept?
Boundary layer separation depends on several things. First of all, like what is the pressure gradient that you are applying. A necessary condition for boundary layer separation is that the pressure gradient must be adverse, but how adverse it is, it depends on the particular flow configuration. If so, dpdx has to be positive, but what is the positive value that is necessary. So, if dpdx is negative, there will be no boundary layer separation, but if dpdx is positive, then depending on the flow configuration, there is no unique answer to this. Depending on the flow configuration, there will be a particular dpdx necessary for which will make sure that the resistance effect is so strong that there is boundary layer separation.
Yes, thank you. Sir, next question. In viscous fluid,
yes.
In viscous fluid, when the fluid is flowing between two parallel plates,
yes,
what are the maximum distance between the plates that by boundary condition can apply?
It does not depend on the thickness of the plate, because the boundary conditions are no slip boundary condition that we have applied. So, no slip boundary condition does not depend on the thickness of the plate. Okay, thank you. Okay. 1178.
Hello.
Yes.
Am I audible?
Yes, you are audible.
So my question is regarding fully developed region.
Yes.
In fully developed region, velocity profile is always parabola or maybe have any other profile?
It may be having any other profile. It depends on whether other body forces are present or not. With a pressure driven velocity field, the fully developed velocity profile is parabolic for a pressure driven flow. But if you have other driving forces like electrical field, magnetic field, if there are several other types of driving forces driving the flow, then it is possible that the velocity profile in the fully developed region may not be parabolic. So, the fully developed velocity profile will be parabolic only when it is a pressure gradient driven flow. Last question 1303. Sorry, you are not audible. Anyway, thank you very much. Thank you very much. We had an enjoyable session, and we come to a closer to this particular session. Yeah, I can take your question. I mean, so many questions are coming, but I can take your question. Yes, your video is there. Please go through your question.
Good evening, sir.
Good evening.
What is the difference between surging and stalling?
I mean, this is a.
Sir, am I audible?
This is a question on aerofoil theory. What is stalling, and this will be covered by Professor Ghosh Maulik when he will talk about potential flows. So, please wait till that time. Okay. So, we had a nice day and a long day. I hope you had enjoyed today's discussion, and we will be back tomorrow morning with the lecture of Professor Ghosh Maulik on the external viscous flows. Thank you very much.